In August 2012, a spacecraft built with 1970s technology, running on less computing power than a modern microwave oven, crossed a boundary that no human-made object had ever crossed before. It left the solar system. The crossing itself took only a few days to complete, but the scientific community spent more than a year arguing about whether it had actually happened, because what the instruments recorded did not match what the models predicted. The solar wind particles vanished. The galactic cosmic ray intensity jumped to a new steady level. The two Voyager spacecraft were launched in 1977 for a 5-year mission to study Jupiter and Saturn. They are still operating in 2026, nearly 50 years later, transmitting data from beyond the edge of the solar system. This is the story of what they discovered, why it mattered, and why the scientists who built the models were wrong in ways they never anticipated. What scientists believed about the edge. Before Voyager crossed it, the edge of the solar system was a theoretical construct built from first principles of plasma physics and magnetohydrodynamics. The basic picture was understood in outline. The Sun continuously emits a stream of charged particles, protons and electrons moving at several hundred kilometers per second in all directions, called the solar wind. This wind was predicted theoretically by Eugene Parker in the late 1950s and confirmed observationally by spacecraft in the early 1960s. Parker showed that the Sun's outer atmosphere, the corona, is so hot that the thermal pressure of the gas exceeds the Sun's gravitational attraction, driving a continuous outflow of plasma into the solar system. The solar wind is not a transient phenomenon associated only with solar storms or active periods. It flows continuously at all times, losing the Sun approximately 1 million tons of mass every second. A number that sounds alarming until you recognize that at this rate, it would take several trillion years for the Sun to lose a significant fraction of its total mass. The solar wind cannot expand forever. Between the stars, space is not empty. The interstellar medium, the gas and dust that fills the galaxy between stellar systems, has its own pressure, its own momentum, its own magnetic field. The density of the interstellar medium is extraordinarily low, approximately 0.1 atoms per cubic centimetre on average, compared to the roughly 10 to the 19th atoms per cubic centimetre of Earth's atmosphere at sea level. The interstellar medium is a better vacuum than any laboratory on Earth can produce. But over the scales relevant to the boundary of the solar system, billions of miles, even this tenuous gas has enough accumulated pressure to stop the solar wind. Where the outward pressure of the solar wind equals the inward pressure of the interstellar medium, a boundary forms. Physicists call this boundary the heliopause. It marks the outermost limit of the solar wind's influence, the point beyond which the Sun's plasma no longer dominates the local environment and the galaxy's plasma takes over. Inside the heliopause is the heliosphere, the vast bubble of space dominated by the Sun's magnetic field, its plasma, its particles. Outside the heliopause is the interstellar medium, dominated by the galaxy's magnetic field, galactic cosmic rays from supernova explosions and other violent events, and plasma that has nothing to do with our star. By the 1980s and 1990s, the theoretical models of this boundary had become sophisticated. Researchers ran three-dimensional magnetohydrodynamic simulations that incorporated the solar wind's velocity and density measured near Earth estimates of the interstellar medium's pressure derived from astronomical observations, and the effects of the Sun's motion through the interstellar medium at approximately 26 kilometers per second, relative to the local standard of rest. These simulations predicted the Helopause would be located at approximately 90 to 100 astronomical units from the Sun, 1 astronomical unit being the distance from Earth to the Sun, approximately 150 million kilometers. At 100 astronomical units, the Helopause would be roughly 15 billion kilometers from the Sun, or about 9.3 billion miles. Before the solar wind reached the Helopause, the models predicted it would encounter a preliminary boundary called the termination shock. The solar wind flows outward at several hundred kilometers per second, supersonic relative to the speed at which pressure disturbances can propagate through the plasma. When this supersonic flow encounters the resistance of the interstellar medium, the physics are analogous to a supersonic aircraft creating a sonic boom as it exceeds the speed of sound in air. The solar wind cannot slow down gradually. It decelerates abruptly at the termination shock, compressing and heating as it transitions from supersonic to subsonic flow. Models place the termination shock at approximately 75 to 90 astronomical units, somewhat inside the Helopause, with the region between the shock and the Helopause called the heliosheath, a turbulent zone of slowed, heated solar wind plasma flowing outward and sideways. The models further predicted that the heliosphere would be approximately symmetric, roughly spherical, perhaps slightly elongated in the direction opposite the Sun's motion through the interstellar medium, forming a tail like the wake behind a moving boat, but basically a bubble of similar dimensions in all directions. The transition across the Helopause was expected to be relatively clean and relatively rapid. Over a few weeks to a few months, the instruments would detect the solar wind plasma disappear. Galactic cosmic ray intensity jump to a higher steady level, and the magnetic field rotate to the orientation of the galactic magnetic field, which was expected to differ substantially from the Sun's magnetic field direction. These predictions were not guesses. They were derived from well-established physics, carefully parameterized with the best available observational data, and refined by multiple independent research groups over decades. The scientists who made them were competent, rigorous, and thorough. They built the best models the available data and computational resources permitted. They published those models in peer-reviewed journals. They taught them to students. They drew diagrams showing the heliosphere as a neat bubble with a symmetric heliopause at a predictable distance. They were wrong about almost everything specific. Not wrong about the basic physics. A heliopause does exist. The termination shock is real. The heliosheath is turbulent. Galactic cosmic rays do intensify beyond the heliopause. The conceptual framework was correct. But every quantitative prediction, every specific number, every detailed description of what the transition would look like turned out to be incorrect in ways that forced fundamental revisions to the models. The Helopause was not at 90 to 100 astronomical units. The heliosphere was not symmetric. The transition did not take weeks. The magnetic field did not rotate at the boundary, and the interstellar medium beyond the Helopause had properties that matched no model's predictions precisely. This is the story of how two spacecraft changed everything we thought we knew. The technology that should have failed. The engineering achievement represented by the Voyager spacecraft cannot be fully appreciated without confronting the specific technical constraints under which they were designed, built, and operated. Constraints that by modern standards seem almost impossibly limiting, yet somehow produce machines that have now been operating continuously for nearly 50 years in one of the most hostile environments in the solar system. Each Voyager spacecraft was built in the early 1970s and weighed approximately 825 kilograms, roughly 1,820 pounds. At launch, including the propellant used for trajectory corrections and orientation adjustments, the spacecraft stood approximately 4 meters high, dominated by a 3.7-meter diameter high-gain antenna dish designed to focus the faint radio signal from the spacecraft's transmitter toward Earth across billions of miles of space. Extending from the main bus were 3 booms carrying scientific instruments and the radioisotope thermoelectric generators that provided electrical power, and a deployable magnetometer boom designed to place the magnetic field sensors far enough from the spacecraft's own weak magnetic field to make accurate measurements of the space environment. The onboard computing systems, which had to handle all spacecraft operations autonomously given the increasingly long communication delays as the spacecraft moved outward, consisted of 3 separate computer systems working in coordination. The computer command subsystem handled incoming commands from Earth and distributed them to the appropriate spacecraft systems. The flight data system collected data from the science instruments and formatted it for transmission back to Earth. The attitude and articulation control system managed the spacecraft's orientation in space, pointing the antenna toward Earth and directing the instrument scan platform toward whatever targets were being observed. Together, these 3 systems had a total memory capacity of approximately 68 kilobytes, an amount of data that would fit comfortably in a single, low-resolution photograph on a modern smartphone, representing millions of times less memory than the device most people carry in their pockets. Despite these constraints, engineers were able to upload new software to the spacecraft decades after launch. In 2002, a software patch was uploaded to Voyager 1 to work around a failing memory module, reprogramming the computer remotely across billions of miles of space. In 2013, engineers successfully reactivated backup thrusters on Voyager 2 that had not fired in 37 years, testing whether the fuel lines had frozen or the valves had seized in the cold of deep space. The thrusters fired correctly on the first attempt. The engineering redundancy built into these spacecraft, the multiple backup systems, the conservative design margins, the meticulous testing, was extraordinary even by contemporary standards. Power is the ultimate constraint that will eventually silence both spacecraft. Each Voyager was launched with 3 radioisotope thermoelectric generators, devices that convert the heat produced by the radioactive decay of plutonium-238 into electricity through solid-state thermoelectric elements. At launch in 1977, each spacecraft's RTG system produced approximately 470 watts of electrical power, enough to run a modest household appliance. Plutonium-238 has a half-life of approximately 87.7 years, which means the power output declines at a steady, predictable rate of roughly 4 watts per year as the radioactive material decays. By 2026, approximately 49 years after launch, The power remaining is approximately 249 watts for Voyager 1, barely enough to operate the remaining active instruments and the transmitter simultaneously. As the power has declined over the decades, engineers at NASA's Jet Propulsion Laboratory have made a continuous series of decisions about which systems to deactivate. The cameras were turned off in 1990 after the famous pale blue dot image because the power and data budget required to operate them could no longer be justified given the absence of planetary targets to photograph. Heaters for various subsystems have been turned off sequentially, allowing components to cool well below their designed operating temperatures. And in some cases, the components have continued to function despite operating far outside their design envelope, a testament to the engineering conservatism built into the original design. The communication system that bridges the gap between the spacecraft and Earth is itself an engineering achievement that deserves separate appreciation. Each Voyager transmits through its high-gain dish antenna, using a radio transmitter with an output power of approximately 23 watts, less than a typical compact fluorescent light bulb. By the time that signal arrives at Earth, after travelling for over 22 hours from Voyager 1's current distance, it has spread across an enormous volume of space. The power arriving at Earth's surface from Voyager 1's transmitter is approximately 10 to the minus 26 watts, 100 septillionths of a watt. Detecting this signal requires the NASA Deep Space Network's largest antennas, 70-metre diameter dish antennas located at 3 sites around the Earth, in California, Spain and Australia, spaced approximately 120 degrees of longitude apart, so that as the Earth rotates, at least one antenna always has a clear view of each spacecraft. The signal processing required to extract meaningful data from a signal this faint against the background of cosmic radio noise is itself a remarkable application of information theory and digital signal processing. The data rate at which Voyager can transmit scientific information back to Earth has declined as the power available for the transmitter has decreased, and as the distance has increased, reducing the signal strength. In the 1980s, during the planetary encounters, Voyager could transmit data at rates of tens of kilobits per second, allowing rapid return of high-resolution images. By 2026, the data rate has declined to tens of bits per second, barely enough to return the slowly varying readings from a handful of instruments monitoring the plasma, magnetic field, and cosmic ray environment of the interstellar medium. But even at these glacial data rates, the instruments are still returning scientifically valuable measurements from a location that no other spacecraft has ever reached. The Grand Tour that changed everything. The original scientific justification for the Voyager program was a rare planetary alignment that occurs once every 176 years. In the late 1970s, the 4 outer giant planets, Jupiter, Saturn, Uranus and Neptune, were positioned in an arc that allowed a single spacecraft, launched at the right time and using the gravitational pull of each planet to redirect and accelerate itself toward the next, to visit all 4 in a single journey without the enormous fuel expenditure that direct trajectories to each planet would require. Without this alignment, visiting all 4 outer planets would have required 4 separate missions, each with its own launch vehicle, its own spacecraft, its own operational team, and its own multi-billion-dollar budget. The alignment made a single mission to all 4 planets possible. The concept of using a planet's gravity to change a spacecraft's trajectory and speed is called a gravity assist, or gravitational slingshot. When a spacecraft approaches a planet, the planet's gravity pulls the spacecraft toward it, accelerating the spacecraft as it falls inward. As the spacecraft swings around the planet and recedes, the planet's gravity decelerates it, but this deceleration operates in a different direction than the initial acceleration, because the spacecraft's trajectory has changed during the encounter. The net result, in the reference frame of the Sun, is that the spacecraft gains velocity from the planet's orbital motion. The planet effectively pulls the spacecraft along with it for a moment, transferring a tiny but significant fraction of the planet's orbital momentum to the spacecraft. Voyager 2 was launched first on August 20th, 1977, on a trajectory that would allow it to make use of all 4 gravity assists if the mission was extended beyond Saturn. Voyager 1 was launched 13 days later, on September 5th, 1977, on a faster trajectory that would reach Jupiter and Saturn earlier than Voyager 2, but that precluded visits to Uranus and Neptune. The faster trajectory was chosen to allow Voyager 1 to make a close flyby of Saturn's moon Titan, which required a trajectory adjustment that bent the spacecraft's path out of the plane of the solar system, away from the remaining planets. The mission architecture required extraordinary precision in trajectory design, executed using computational resources that were primitive by current standards, but represented the cutting edge of numerical analysis in the 1970s. The trajectory calculations had to account for the gravitational influences of all the planets, the solar wind's effect on the spacecraft's solar panels and structure, the tiny thrust produced by each thruster firing for attitude control, and the perturbations caused by thermal expansion and contraction of the spacecraft's structure as it moved between sunlit and shadowed orientations. The calculations were accurate enough that the gravity assist maneuvers at Jupiter and Saturn executed with the precision needed to redirect the spacecraft toward Uranus and Neptune. A chain of trajectory correction spanning billions of miles and many years, each dependent on the accuracy of the previous one. The mission was formally named the Voyager Interstellar mission by NASA after it became clear that both spacecraft would remain functional long after their planetary encounters ended. But the planetary phase of the mission, the years between 1979 and 1989, when the spacecraft were conducting their flybys of the outer planets, was itself a scientific revolution that transformed planetary science more thoroughly than any previous or subsequent set of missions. Before Voyager, the outer planets and their moons were known primarily through Earth-based observations using optical telescopes, supplemented by limited data from the Pioneer 10 and Pioneer 11 spacecraft that had preceded Voyager to Jupiter and Saturn, but carried less sophisticated instrument suites. From Earth, even the largest telescopes of the 1970s could resolve Jupiter's disk and observe the major cloud bands and the Great Red Spot, but the level of detail was limited. Saturn's rings were known to consist of multiple components separated by gaps, but their internal structure was completely unknown. Jupiter's 4 Galilean moons, Io, Europa, Ganymede, and Callisto, were observed as tiny disks at best, their surface features invisible, and their geological nature entirely unknown. Uranus and Neptune were essentially featureless disks even in the best ground-based observations. What Voyager revealed at each of these destinations was not merely a higher resolution version of what was already known. It was a qualitatively different picture, a picture containing phenomena that no prior observation had suggested, and that theoretical models of planetary formation and evolution had not predicted. The discoveries at Jupiter alone would have justified the entire program. The discoveries at Saturn added another revolution, and the discoveries at Uranus and Neptune, where Voyager 2 was the first and remains the only spacecraft ever to visit, added entirely new categories of scientific knowledge to the planetary science literature. Io and the discovery of alien volcanism. Before Voyager 1's encounter with Jupiter's moon Io in March 1979, the prevailing scientific expectation for the surface of Io was essentially indistinguishable from the expectation for Earth's moon, a cold, geologically dead world, cratered and inert, its surface unchanged for billions of years. This expectation was reasonable, given what was known. Io is roughly the same size as Earth's moon, approximately 3,640 kilometers in diameter. It orbits Jupiter at a distance of approximately 422,000 kilometers, closer to Jupiter than our own moon is to Earth. From Earth-based observations, Io showed an unusually red-orange color compared to the other Galilean moons, and its spectrum showed evidence of sulfur compounds on its surface, but neither observation was obviously indicative of geological activity. The standard model of rocky body formation and evolution suggested that a moon of Io's size should have cooled and solidified billions of years ago, its interior too cold for volcanic activity to persist. 3 researchers, Stanton Peele, Patrick Casson and Ray Reynolds, published a theoretical paper in the journal Science on March 2, 1979, the day before Voyager 1 made its closest approach to Io. The paper calculated the rate of tidal heating in Io's interior and concluded that the heat generated by the constantly changing tidal forces exerted by Jupiter, amplified by the gravitational interaction with Europa and Ganymede, that keeps Io's orbit slightly eccentric rather than perfectly circular, would be sufficient to melt Io's interior and maintain active volcanism at the surface. The paper concluded with a prediction. Voyager should find Io to be volcanically active. Voyager exceeded even this prediction. Linda Morabito, a navigation engineer at the Jet Propulsion Laboratory, who was examining Voyager 1 images of Io to determine precise spacecraft position, noticed something in the image that had not been expected in navigation imagery. Extending beyond the limb of Io, the edge of the moon's disk, was a large umbrella-shaped structure, clearly not an artifact of the imaging process, that could only be interpreted as a volcanic plume erupting from the surface. The plume was subsequently identified as originating from a volcanic feature later named Pele, and its eruption column extended approximately 300 kilometers above the surface, far higher than any volcanic eruption ever observed on Earth. Io turned out not to have one active volcano, it had hundreds of them. Voyager 1 and Voyager 2, which arrived at Jupiter in July 1979, approximately 4 months after Voyager 1, together documented 9 active volcanic eruptions during their flybys. Later observations, first from Earth-based infrared telescopes that could detect Io's thermal emission, and subsequently from the Galileo spacecraft that orbited Jupiter in the 1990s, revealed that Io has more than 400 known volcanic centers, making it the most volcanically active body in the solar system by an enormous margin. More active per unit surface area than Earth. More active in terms of total heat flow than any other planetary body. The surface of Io showed no impact, craters at all, a complete absence of the ancient bombardment record that defines the surfaces of geologically dead bodies, like Earth's moon or Mars's ancient highlands. The absence of craters is diagnostic. It means the surface is young, constantly being resurfaced by volcanic deposits that bury and obliterate any impact features before they can accumulate. The Voyager images revealed a landscape of bizarre colors, yellow, orange, red, white, and black, produced by various forms of sulfur and sulfur dioxide frost deposited from the volcanic plumes and lava flows. Some regions showed active lava flows with temperatures measured at over 1,600 degrees Celsius, hotter than typical basaltic eruptions on Earth and consistent with ultramafic compositions that have not erupted on Earth in billions of years. The mechanism driving Io's volcanism, tidal heating from the competing gravitational tugs of Jupiter, Europa, and Ganymede was confirmed as the energy source by the agreement between the measured heat flow from Io's surface and the theoretical calculations of Peale, Casson, and Reynolds. This confirmation had immediate and profound implications beyond Io itself. It established that tidal heating is a major and potentially dominant geological energy source for moons orbiting giant planets. This recognition transformed the scientific assessment of habitability in the outer solar system, because tidal heating operates entirely independently of solar energy, meaning that moons far from the Sun, where sunlight is too weak to warm liquid water on a planetary surface, can nevertheless maintain liquid water in their interiors if their orbital dynamics produce sufficient tidal dissipation. The discovery of Io's volcanism was therefore not just a discovery about one specific moon. It was a discovery about the category of energy sources available to planetary bodies throughout the universe, with consequences that extended directly to the assessment of Europa, Enceladus, and dozens of other potentially habitable ocean worlds. Europa and the first hint of another ocean. Europa, the second of Jupiter's 4 large Galilean moons, received comparatively brief attention during Voyager 1's flyby in March 1979. The encounter geometry was not optimized for Europa observation, and the mission's primary targets at that point were Io and Jupiter itself. Voyager 2's flyby in July 1979 provided somewhat better coverage, though still at relatively large distances compared to what would later be achieved by the Galileo mission. What the Voyager images showed was nevertheless sufficient to establish that Europa was one of the most scientifically extraordinary objects in the solar system. Europa is slightly smaller than Earth's moon, approximately 3,122 kilometers in diameter. Its surface is covered in ice. This was expected. At Europa's distance from Jupiter, and correspondingly from the Sun, water ice is the natural surface material, just as rock and regolith are the natural surface materials of bodies in the inner solar system, where temperatures are too high for ice to be stable. What was not expected was the character of the ice surface. Europa's surface showed almost no impact craters, far fewer than any model of the outer solar system bombardment rate would predict for a geologically dead, icy body. The absence of craters meant the surface was young, just as Io's absence of craters meant Io's surface was constantly renewed. But Io's surface is renewed by volcanic eruptions producing lava flows that bury old terrain. Europa's surface showed no volcanic features. The renewal mechanism was different. What Voyager revealed instead was a network of linear features, dark lines crossing the surface in complex intersecting patterns. Some were long, straight cracks extending for hundreds of kilometers. Others were broader bands, sometimes showing apparent offset between the ice on either side, suggesting that the crust had fractured and the two halves had shifted relative to each other before refreezing. Some regions of the surface showed chaotic terrain, areas where the ice appeared to have broken into irregular blocks that had rotated and tilted before being frozen into new positions. The blocks preserving the surface markings of the surrounding undisturbed ice in ways that allowed researchers to reconstruct the original arrangement by fitting the pieces back together like a three-dimensional puzzle. The interpretation of these features was not immediately obvious from Voyager's limited coverage, but the most natural explanation, the one that fit all the observations consistently, was that Europa's ice crust was floating on a layer of liquid water. The linear cracks would form where the ice was being pulled apart by tidal flexing, and the underlying liquid water welled up to fill the gap before refreezing. The chaos terrain would form where localized heating from below, perhaps from the convection of warm water or the upwelling of a warm diapir of ice, had melted the surface ice from beneath, allowing the ice blocks to float on the underlying water before refreezing into their disordered positions. The relative youth of the surface, indicated by the absence of craters, would reflect the constant resurfacing produced by this geological activity. The energy source for this activity would be tidal heating, operating through the same mechanism that drives Io's volcanism but at lower intensity. Europa's orbital eccentricity, maintained by its gravitational resonance with Io and Ganymede, generates tidal flexing that dissipates as heat in Europa's interior. The heat is insufficient to produce the runaway volcanism of Io, but theoretical calculations suggested it could be more than enough to maintain a global liquid water ocean beneath an ice crust of perhaps tens of kilometers thickness. The Voyager images were not definitive proof of a subsurface ocean. The coverage was incomplete, the resolution limited, and the interpretation involved theoretical modelling that could in principle have alternatives. The definitive evidence came from the Galileo spacecraft, which arrived at Jupiter in 1995 and spent 8 years making repeated flybys of all 4 Galilean moons, with instruments specifically designed to test the ocean hypothesis. Galileo's magnetometer detected an induced magnetic field at Europa, a field generated by the interaction of Jupiter's rotating magnetic field with a conducting layer within Europa, consistent with a global ocean of salty liquid water at relatively shallow depth beneath the ice surface. This magnetic evidence, combined with the geological evidence from Voyager and Galileo's own imaging, established Europa's subsurface ocean as one of the most thoroughly supported conclusions in planetary science. But the scientific journey toward that conclusion began with Voyager's images of Europa's bizarre, craterless, fractured surface. The recognition that an icy moon could harbour a liquid water ocean, that the ingredients for potentially habitable environments existed not just at comfortable distances from stars in stellar habitable zones, but in the frigid outer solar system heated by tidal flexing, was among the most consequential conceptual shifts in the history of astrobiology. The subsequent explosion of interest in ocean worlds, Europa, Enceladus, Titan, Ganymede, Callisto, and potentially dozens of similar moons around outer planet systems throughout the galaxy, traces directly to the images that Voyager 1 and Voyager 2 returned from their flybys of Europa in 1979. Saturn's rings were 1,000 times more complex than anyone knew. Saturn's rings had been observed from Earth since Galileo first noticed in 1610 that Saturn appeared to have companions on either side, what he described as handles or ears, which he could not resolve into rings with his primitive telescope. Christian Huygens in 1655 was the first to correctly identify the ring system as a flat disk surrounding the planet and not in contact with it. By the late 1970s, ground-based telescopes had resolved the ring system into several distinct components: the bright B ring, the slightly less bright A ring, the fainter C ring, and the Cassini division, a dark gap between the A and B rings where the ring material appeared to be sparse or absent. Additional fainter ring components had been detected by infrared observations and by the Pioneer 11 spacecraft that preceded Voyager to Saturn. The rings were understood to consist of particles orbiting Saturn individually, each following its own Keplerian orbit, with the apparent banding structure produced by variations in particle density across the ring system. The particles were known from spectroscopic observations to be composed primarily of water ice. The overall picture was of a relatively simple system, a few broad bands of icy particles, some gaps between them, a handful of features that could be explained by gravitational resonances with Saturn's inner moons. When Voyager 1 flew through the Saturn system in November 1980 and the cameras began transmitting close-up images of the rings, the reaction among planetary scientists was one of astonishment at a level that has rarely been equalled in the history of space exploration. The rings were not simple. They were extraordinarily complex, structured at every scale that the cameras could resolve, and filled with features that existing theories of ring dynamics could not explain. What had appeared from Earth as a few broad rings separated by a few gaps was revealed to be thousands of individual narrow ringlets. The Voyager images showed structure down to the resolution limit of the cameras, and scientists immediately recognized that still smaller structure probably existed below that limit. The Cassini division, which had appeared from Earth to be an empty gap in the ring system, was found to contain rings of its own, faint but clearly present. The apparent emptiness of the Cassini division, seen from Earth, reflected not the total absence of ring material, but the contrast between the faint ringlets within it and the dense bright rings on either side. More puzzling than the ringlets were the other structures that Voyager discovered. Spokes appeared in the B ring, dark radial features stretching outward from the inner edge of the ring, sometimes thousands of kilometers long, that rotated with Saturn's magnetic field rather than with the orbital period of the ring particles themselves. This was impossible according to standard orbital mechanics. Ring particles at different distances from Saturn orbit at different speeds. Particles closer to the planet move faster. Particles farther out move slower, in strict accordance with Kepler's laws. A radial feature should therefore be rapidly sheared apart by this differential rotation, with the inner end moving faster than the outer end, destroying the radial alignment within hours. Yet spokes persisted for days. The explanation eventually settled on involves electrically charged dust particles being levitated above the ring plane by electromagnetic forces associated with Saturn's magnetic field, allowing them to co-rotate with the field rather than following Keplerian orbits. But this mechanism was not understood until years after Voyager's discovery. The F ring, a narrow ring just outside the main A ring, showed braided structure, multiple strands that appeared to twist around each other in a complex interweaving pattern unlike anything seen elsewhere. Flanking the F ring were two small shepherd moons, Prometheus and Pandora, whose gravitational influence was understood to confine the ring material and prevent it from spreading outward and inward. But the specific braided structure of the F ring, which changed over time as subsequent observations by the Cassini spacecraft would reveal, resulted from the perturbative influence of these shepherd moons on the ring particles in ways that are still not fully understood. The detail revealed by Voyager's ring observations established Saturn's ring system as one of the most scientifically rich environments in the solar system, a natural laboratory for studying orbital mechanics, fluid dynamics, wave propagation, and gravitational interactions at scales ranging from individual particles to continent-sized structures. The discoveries drove a generation of theoretical work on the physics of planetary rings, with implications extending far beyond Saturn to the rings of Uranus and Neptune that Voyager 2 would subsequently discover, to the protoplanetary disks around young stars from which planetary systems form, and to the accretion disks around black holes and neutron stars. The complexity of Saturn's rings was not a curiosity confined to one planet. It was a window into fundamental physical processes operating throughout the universe wherever gravity organizes rotating material into disks. Titan and the world with weather. Among all the targets in Saturn's system, Titan held a special scientific interest that had been building since Gerard Kuiper detected methane in its spectrum in 1944. This spectroscopic detection established that Titan, Saturn's largest moon, possessed an atmosphere, the only moon in the solar system known at the time to have one. By the late 1970s, infrared observations had detected additional atmospheric constituents, including nitrogen, ethane, and acetylene, suggesting that Titan's atmosphere was thick and chemically complex. But the exact composition, the surface pressure, and the nature of the surface beneath the atmosphere were entirely unknown. The Voyager 1 mission architects made a specific and consequential decision. They would adjust Voyager 1's trajectory to make a close flyby of Titan, passing within approximately 4,000 kilometers of its surface, even though this trajectory choice would bend Voyager 1's path out of the plane of the solar system and prevent any subsequent visit to Uranus and Neptune. The scientific promise of Titan was judged sufficient to justify sacrificing the opportunity to visit the ice giants. Titan's surface was completely hidden beneath a thick orange-brown photochemical haze produced when solar ultraviolet radiation broke apart nitrogen and methane molecules in the upper atmosphere, allowing the fragments to recombine into more complex organic compounds. The haze particles scattered sunlight to produce the orange glow that made Titan distinctive in Voyager's images. At visible wavelengths, the surface was completely inaccessible to Voyager's cameras. What Voyager could measure was the atmosphere itself, its temperature and pressure as functions of altitude, its chemical composition, and the properties of the haze layer. These measurements revealed a world with extraordinarily complex atmospheric chemistry. The photochemical reactions producing the haze operated through a cascade of steps, beginning with the dissociation of methane by solar ultraviolet photons and producing dozens of organic compounds including ethane, propane, acetylene, ethylene, and hydrogen cyanide, among others. The variety and complexity of the organic chemistry was remarkable, and its similarity to the kind of organic chemistry thought to have operated on early Earth before life arose and before the oxygen atmosphere that now largely prevents such chemistry made Titan scientifically fascinating as a potential analogue to prebiotic Earth. Theoretical models developed from Voyager's atmospheric data predicted that Titan's surface might host lakes or seas of liquid methane and ethane, produced by a methane cycle on Titan analogous to Earth's water cycle. Methane evaporating from the surface, forming clouds in the troposphere, precipitating as methane rain, and flowing back to the surface through rivers and streams. The temperature at Titan's surface was measured at approximately -179 degrees Celsius, cold enough for water ice to be as hard as rock, but within the range where liquid methane could exist. The Cassini-Huygens mission, which arrived at Saturn in 2004, confirmed this prediction spectacularly. The Huygens probe that descended through Titan's atmosphere in January 2005 photographed river channels, floodplains, and rounded stones consistent with fluvial erosion by liquid hydrocarbons, while Cassini's radar mapping revealed extensive lakes and seas of liquid methane and ethane in the polar regions, Uranus, Neptune, and the end of the planetary mission. While Voyager 1 proceeded outward from Saturn on its trajectory toward the Helopause, Voyager 2 continued the planetary tour. In January 1986, Voyager 2 arrived at Uranus, the seventh planet from the Sun, and before Voyager's arrival, one of the least understood bodies in the solar system. Even the most basic properties of Uranus were poorly known. Its magnetic field had never been detected, its interior composition was uncertain, and the nature of its ring system, discovered serendipitously by Earth-based observers in 1977 during a stellar occultation, was almost completely uncharacterized. The most immediately striking property of Uranus, already known from Earth-based observations, is its extreme axial tilt. While Earth's rotational axis is tilted approximately 23.5 degrees relative to the perpendicular of its orbital plane, Uranus's axis is tilted approximately 98 degrees, more than a right angle relative to its orbital plane. Uranus effectively rotates on its side, with its poles alternately pointing toward and away from the Sun during its 84-year orbit. This geometry meant that at the time of Voyager 2's encounter in 1986, the south pole of Uranus was pointing almost directly at the Sun, and the equatorial regions were in perpetual twilight. This created the most unusual observational geometry of any planetary encounter in the Voyager mission. Voyager 2's observations revealed a magnetic field whose geometry was completely unlike anything seen at any other planet. Rather than a dipole field roughly aligned with the rotation axis, as at Earth, Jupiter, and Saturn, Uranus's magnetic field is tilted approximately 60 degrees relative to its rotation axis and is displaced from the planet's center by approximately 1/3 of the planetary radius. This configuration produces an extraordinarily complex magnetospheric structure that tumbles end over end with each planetary rotation, creating conditions that change drastically over the course of Uranus's 17-hour day. The atmosphere of Uranus appeared relatively bland compared to Jupiter's complex cloud structure. A nearly uniform pale blue color produced by the absorption of red light by methane in the upper atmosphere, with few visible cloud features at the spatial resolution of Voyager's cameras. Wind speeds were measured at up to approximately 250 meters per second, faster than most terrestrial storms, but substantially slower than the wind speeds measured subsequently at Neptune. Neptune, which Voyager 2 reached in August 1989 after a 4-year journey from Uranus, turned out to be strikingly more dynamic than Uranus, despite being significantly colder. Neptune receives only about 40% as much solar energy per unit area as Uranus because of its greater distance from the Sun. The most prominent atmospheric feature was the Great Dark Spot, an anticyclonic storm system roughly the size of Earth located in Neptune's southern hemisphere, analogous in some respects to Jupiter's Great Red Spot. Surrounding the Great Dark Spot were cirrus-like clouds of methane ice that cast shadows on the cloud deck below, allowing the altitude difference between the clouds and the deck to be measured. Wind speeds at Neptune's cloud tops were measured at up to approximately 600 meters per second, the fastest winds ever measured on any planet in the solar system. Triton, Neptune's largest moon, presented the final major discovery of the Voyager planetary mission. Triton orbits Neptune in the retrograde direction, opposite to the direction of Neptune's rotation, which is unique among large moons in the solar system and indicates that Triton was not formed alongside Neptune, but was captured from the outer solar system. The surface temperature of Triton was measured at approximately 38 Kelvin, one of the coldest surfaces ever measured anywhere in the solar system. Yet despite this extreme cold, Triton was geologically active. Voyager's cameras detected dark plumes erupting from the surface and rising several kilometers before being blown downwind to deposit dark streaks on the surface. These eruptions were driven by the sublimation of nitrogen ice heated by solar radiation, which builds pressure beneath an overlying cap of translucent nitrogen ice until the cap ruptures and the nitrogen vents into space. With Triton, the planetary phase of the Voyager mission effectively concluded. Both spacecraft were still functional, still transmitting data, still capable of scientific measurement, and they were heading outward, toward the termination shock, the heliosheath, and ultimately the Helopause that waited at the edge of the solar system. The journey that would produce the most scientifically consequential and the most completely unexpected discoveries of the entire mission was just beginning. The termination shock was in the wrong place. Scientists predicted the termination shock would be encountered at approximately 75 to 90 astronomical units from the Sun. Voyager 1 crossed the termination shock on December 16, 2004, at a distance of approximately 94 astronomical units, already beyond the predicted range. But the story of the termination shock crossing was considerably stranger than simply finding it farther out than expected, because Voyager had been detecting the shock signatures for more than 2 years before the final crossing occurred. The first indication that Voyager 1 was approaching the termination shock came in August 2002, when the spacecraft was at approximately 85 astronomical units within the predicted range for the shock. The plasma instruments and the cosmic ray detectors began showing signatures consistent with approaching a shock boundary. The intensity of anomalous cosmic rays, ions of interstellar origin that had been accelerated by the shock, began increasing. The magnetic field showed signatures of compression. Everything suggested the termination shock was nearby. And then, over the following months, the signatures disappeared. The shock had moved outward faster than Voyager was moving, carrying the boundary away from the spacecraft. This breathing behavior of the termination shock, its expansion and contraction in response to the variations in solar wind output associated with the 11-year solar activity cycle, had been predicted in qualitative terms. The termination shock is a pressure balance boundary, and its position responds to changes in the pressure on either side. When the Sun is at solar maximum and the solar wind output is elevated, the increased outward pressure pushes the termination shock farther from the Sun. When solar activity decreases and the solar wind weakens, the shock moves inward. But the magnitude of these oscillations, large enough that Voyager could find itself inside and outside the shock multiple times as it approached, was larger than models had anticipated. Voyager 1 detected the termination shock again in 2003, again at approximately 85 astronomical units. And again, the shock moved away before the spacecraft could make a definitive crossing. The pattern of repeated approaches and retreats continued until December 2004, when Voyager crossed the termination shock at 94 astronomical units and remained in the heliosheath, the region beyond the shock, permanently. Voyager 2 crossed the termination shock on August 30th, 2007 at approximately 84 astronomical units, roughly 10 astronomical units closer to the Sun than Voyager 1's crossing. This discrepancy was the first solid evidence that the heliosphere is not symmetric. If the heliosphere were a simple sphere, both spacecraft crossing in different directions but both heading generally outward from the Sun, should encounter the termination shock at approximately the same distance. Finding the shock 10 astronomical units closer in Voyager 2's direction than in Voyager 1's direction implied that the heliosphere is compressed in some directions and extended in others. Voyager 1 was heading generally toward the nose of the heliosphere, the direction in which the Sun is moving through the local interstellar medium. The nose is compressed by the ram pressure of the interstellar headwind, analogous to the bow wave in front of a moving boat. Voyager 2 was heading more toward the flank of the heliosphere, where the compression from the Sun's motion is less severe, and the heliosphere can extend farther. The 10 astronomical unit discrepancy in shock crossing distances between the two spacecraft confirmed that the heliosphere has an asymmetric, blunted nose shape rather than the symmetric bubble that models had described. Beyond the crossing distance, the properties of the termination shock itself differed from predictions. Models expected the shock to accelerate particles efficiently, producing a population of energetic ions that would be detectable well inside the heliosheath. The observation showed a shock that was less efficient at particle acceleration than predicted, with the anomalous cosmic ray population that should have been strongly enhanced at the shock showing a smaller increase than expected. The reasons for this reduced acceleration efficiency are still debated, but they pointed to aspects of shock physics that the models had not correctly captured. The heliosphere is the wrong shape. The confirmation that the termination shock crossings occurred at different distances in different directions was not merely a detail about the precise geometry of one boundary. It established that the fundamental premise underlying most pre-Voyager models of the heliosphere, the assumption that the heliosphere is approximately spherical, was incorrect. The heliosphere is not a bubble. It is an asymmetric structure whose shape reflects the interplay between the solar wind's outward pressure and the ram pressure and magnetic pressure of the interstellar medium flowing past it. The analogy that most accurately captures the heliosphere's actual shape is that of a blunt-nosed projectile or a bullet moving through a fluid. In the direction of the Sun's motion through the interstellar medium, the nose direction toward which Voyager 1 was heading, the interstellar headwind compresses the heliosphere, flattening the nose into a blunt, rounded front. The heliosheath in this direction is relatively thin. The distance between the termination shock and the helipause is smaller than in other directions because the increased external pressure pushes both boundaries inward. Perpendicular to the Sun's motion, the compression is less severe, allowing the heliosphere to extend farther in those directions. In the tail direction, opposite to the Sun's motion, the heliosphere stretches out into an extended wake, analogous to the tail of a comet or the downstream wake of a boat moving through water. The extent of the heliospheric tail is unknown. Theoretical models predict it extends for hundreds or possibly thousands of astronomical units, far beyond anything that either Voyager spacecraft will reach in any foreseeable future. The Voyagers have provided direct measurements at two specific locations, near the nose in Voyager 1's case and toward the flank in Voyager 2's case. These two data points constrain the shape in those regions, but they leave enormous uncertainties about the tail and about variations in the heliosphere's shape over time as the solar activity cycle modulates the solar wind's total output. The shape of the heliosphere has consequences that extend beyond mere geometry. The heliosphere serves as a partial shield for the inner solar system against galactic cosmic rays, high-energy particles from supernova explosions, and other violent astrophysical events that pervade the interstellar medium. The efficiency of this shielding depends on the heliosphere's size and shape. A larger heliosphere provides more total shielding volume. An asymmetric heliosphere provides less uniform shielding. Cosmic rays can penetrate more easily from some directions than others. The tail of the heliosphere, if it extends for hundreds of astronomical units, might provide an easier pathway for cosmic rays to reach the inner solar system from the anti-nose direction. Over geological timescales, the heliosphere's shape and size have varied as the Sun has moved through regions of the interstellar medium with different densities and pressures. The Sun is currently passing through a region called the local interstellar cloud, a slightly denser patch of the interstellar medium several light years across. As the Sun exits this cloud, an event expected in a few thousand years, the external pressure on the heliosphere will change, altering its size and shape. During periods when the Sun was passing through denser interstellar medium, the heliosphere would have been compressed inward, potentially allowing more galactic cosmic rays to penetrate to Earth. The correlation between the Sun's passage through different interstellar environments over its galactic orbit and the history of cosmic ray exposure on Earth, potentially recorded in geological isotope records, represents an active area of research that Voyager's shape measurements have made more quantitative. The transition was nothing like the models predicted. Every model of the heliosphere produced before Voyager reached the boundary described the transition from the heliosheath into interstellar space as a relatively rapid and clean event. The spacecraft would detect the solar wind plasma disappearing over a period of weeks to months. Galactic cosmic ray intensity would jump sharply to a new, higher steady level. The magnetic field would rotate to the orientation of the galactic magnetic field. These changes would occur in close temporal succession, perhaps in a different order depending on the specific model, but all within a relatively compact interval of time. The transition zone, the Helopause itself, was expected to be a thin boundary, not a diffuse region of gradual transition. What Voyager 1 actually experienced beginning in 2010, more than 2 years before the eventual Helopause crossing, was a prolonged, complex, and structurally rich process that contradicted every aspect of the clean transition picture. Starting in 2010, when Voyager 1 was at approximately 113 astronomical units, the instruments began detecting changes that should not have been occurring in the middle of the heliosheath. Galactic cosmic rays, high-energy particles from interstellar space that the heliosphere partially shields the inner solar system from, began increasing in intensity. Simultaneously, the anomalous cosmic rays that had been accelerated at the termination shock began decreasing. Both of these trends moved in the direction expected at the Helopause. Galactic cosmic rays should increase, termination shock products should decrease, but neither trend should have been happening at this location. Voyager was still clearly in the heliosheath. The plasma instruments were still detecting solar wind material. The magnetic field still had the characteristics of the heliospheric field. The spacecraft was not at the Helopause, yet the particle environment was already beginning to look like the particle environment beyond the Helopause. The explanation, eventually developed to account for these early changes, involved the concept of a depleted zone, a region of the outer heliosheath where the density of solar wind particles was lower than in the inner heliosheath, allowing galactic cosmic rays to penetrate inward before the Helopause itself was crossed. The outer heliosheath is the region just inside the Helopause, where the solar wind plasma has been slowed, compressed, and heated by the termination shock and is flowing sideways in an attempt to deflect around the obstacle of the interstellar medium pressure. In this region, the flow patterns are turbulent and complex, and the particle distribution is far from uniform. Areas of particularly low solar wind density could allow galactic particles to seep inward, explaining the gradual increase that Voyager was detecting. Then, in June 2012, something happened that no model had predicted at all. Voyager 1 entered a region where the magnetic field lines aligned precisely in the radial direction, pointing directly outward from the Sun, unlike the turbulent and variably directed field of the heliosheath. The particles flowing along these radially aligned field lines were remarkable, solar wind particles flowing outward and galactic cosmic rays flowing inward, using the same magnetic channels simultaneously, as if the field lines were highways connecting the interior of the heliosphere directly to interstellar space. The scientists at the Voyager mission immediately recognized that this was not a feature any existing model of the heliosphere described. They named it the magnetic highway. The magnetic highway is now understood to represent a region where the Sun's magnetic field lines have connected to the galactic magnetic field lines through a process called magnetic reconnection. The same process that drives solar flares and coronal mass ejections when magnetic field lines of opposite polarity come together and snap into new configurations, releasing enormous amounts of energy. At the Helopause, the solar magnetic field and the galactic magnetic field are pressing against each other from opposite sides. Where the geometries are favourable, where the two field systems are oriented in ways that allow them to reconnect, field lines from both systems merge into continuous structures that span the boundary, creating the channels that particles can follow in either direction. The magnetic highway is the physical manifestation of this reconnection, and its existence was a discovery that fundamentally changed the understanding of how the heliosphere and interstellar space interact. Voyager 1 spent approximately 2 months in the magnetic highway between June and August 2012. During this period, cosmic ray intensities were higher than anywhere else in the outer heliosheath, and solar particle intensities were lower. The spacecraft was sampling a region with direct physical connectivity to interstellar space, even though it had not yet, in any conventional sense, crossed the Helopause. The boundary between the solar system and interstellar space was not a clean line to be crossed in a moment. It was a zone of complex, patchy, physically rich transition that was fundamentally different from anything the theoretical community had imagined. On August 25, 2012, the transition completed. Solar wind plasma essentially vanished from the instruments. The galactic cosmic ray intensity jumped to a steady high level that it has maintained ever since, with only small fluctuations. These changes happened over a period of just a few days, far more rapidly than the gradual trends that had been building for 2 years beforehand, and in the direction opposite to what the magnetic highway period might have suggested. The boundary, in its final form, was sharper than the preceding years of gradual change had implied. Voyager 2's crossing on November 5, 2018, was both similar and different. The crossing itself happened over approximately 1 day, faster than Voyager 1's transition by a substantial margin. The plasma instrument on Voyager 2, which had failed on Voyager 1 before the crossing, was still functional and provided direct measurements of the transition in the solar wind plasma density, which dropped by a factor of more than 20 within a single day as the spacecraft passed through the Helopause. The Voyager 2 crossing also showed a clearer magnetic field rotation than Voyager 1, approximately 36 degrees over the crossing interval, though this was still far less than the dramatic reorientation that models had predicted. The different character of Voyager 2's crossing compared to Voyager 1's, faster, cleaner, with a measurable field rotation, reflects the fact that the two spacecraft crossed at different locations on the Helopause, where the boundary had different structural properties. The Helopause is not uniform. It has regions of different thickness, different magnetic geometry, and different dynamical behavior. And the specific crossing experience of each spacecraft depended critically on where on this complex surface the crossing occurred. Both spacecraft also experienced the phenomenon of crossing the Helopause and then briefly being pulled back inside. Voyager 1 detected a brief return of solar wind signatures in August 2013, nearly a year after its crossing, when a pulse of solar wind travelling outward through the heliosphere hit the Helopause and temporarily pushed it outward, past Voyager's position. The boundary expanded across the spacecraft, then contracted as the pulse dissipated, dropping Voyager back into interstellar space. This oscillation of the Helopause, its breathing motion in response to solar wind variability, meant that defining a precise moment when a spacecraft left the solar system was philosophically as well as physically complicated. The boundary is not a fixed wall. It is a dynamic membrane that expands and contracts in response to conditions on both sides, and a spacecraft near the boundary can find itself on one side or the other multiple times without actually moving in the conventional sense. The accumulated picture of the Helopause that emerged from Voyager's observations is of a boundary that is real and physically meaningful. Plasma properties, particle populations, and magnetic field characteristics are genuinely different on either side. But that is also complex, inhomogeneous, dynamically variable, and structured in ways that required entirely new theoretical frameworks to understand. The clean, sharp, rapidly crossed boundary of the models was replaced by a picture of a patchy, breathing, magnetically rich transition zone, with internal structure that the models had not anticipated, and that will require future missions specifically designed to characterize it before it is fully understood. The magnetic highway nobody saw coming. The magnetic highway was perhaps the single most unexpected specific discovery in Voyager's entire history at the boundary. To appreciate why, it is necessary to understand how theoretical physicists in the decades before Voyager's crossing had expected the magnetic fields on either side of the Helopause to relate to each other, and why a structure connecting them was thought to be unlikely or impossible. The heliosphere is filled with the Sun's magnetic field. This field originates at the Sun's surface, carried outward by the solar wind into interplanetary space. As the Sun rotates, completing one rotation roughly every 25 days at its equator, the magnetic field it carries outward is wound into a spiral pattern, like water from a rotating lawn sprinkler. At large distances from the Sun, this spiral becomes nearly tangential rather than radial, meaning the field lines run roughly perpendicular to the direction from the Sun rather than pointing toward it. Within the heliosphere, this spiral field structure, called the Parker spiral after Eugene Parker, who first described it theoretically, defines the overall orientation of the magnetic field, though turbulence and the complex dynamics of the heliosheath substantially perturb it. Outside the Helopause, the galactic magnetic field has a completely independent origin. It is generated by the collective motion of charged particles throughout the Milky Way galaxy, by the rotation of the galaxy itself, and by the turbulent dynamo processes associated with supernova explosions and stellar winds distributed throughout the disk of the galaxy. The local galactic magnetic field, the field in the immediate vicinity of the solar system, has a strength of approximately 5 to 6 nanotesla and is oriented in a direction that is distinct from the heliospheric field direction. Pre-Voyager models predicted that these two magnetic field systems would be separated by the helipause, with the solar field on one side and the galactic field on the other, and that the transition between them would occur across the helipause itself. In the simplest version of this picture, the two field systems would be completely independent until the moment of crossing. The helipause would act as a magnetic barrier separating the solar field domain from the galactic field domain, and particles from either side would be unable to cross without also crossing the helipause. This picture implied that galactic cosmic rays could only enter the heliosphere by diffusing across the helipause, a relatively slow process governed by the gradients in the cosmic ray pressure across the boundary. It implied that solar particles could only escape the heliosphere by the same diffusion process. And it implied that the transition at the helipause should be sharp. No solar particles on the interstellar side, no galactic cosmic rays on the heliospheric side. The magnetic highway violated all of these implications simultaneously. In the region Voyager entered in June 2012, solar particles and galactic cosmic rays were coexisting in the same volume of space, flowing in opposite directions, along the same magnetic field lines. The field lines themselves were radially oriented, pointing directly outward from the Sun, in a way that was geometrically inconsistent with either the turbulently structured heliosheath field or the galactic field measured after the crossing. The highway represented a region where neither the solar field nor the galactic field was dominant, but where both had somehow merged into a hybrid structure that provided direct physical connectivity across what was supposed to be an impermeable boundary. The mechanism that produces this structure is magnetic reconnection, which in the context of the helipause involves a specific geometric configuration. Where the solar magnetic field and the galactic magnetic field approach the helipause from opposite sides in anti-parallel directions, the fields pointing in exactly opposite ways. The energy density in the combined field is minimized if the fields annihilate each other, rather than simply pressing together. Quantum mechanically, this annihilation releases energy and produces a new field configuration in which the solar and galactic field lines have merged into continuous U-shaped structures that are anchored on one end in the Sun's field domain and extend into the galactic field on the other. Particles can flow along these merged field lines from the solar side to the galactic side, and vice versa, without encountering any physical barrier. Magnetic reconnection is a well-established physical process. It has been studied extensively in the laboratory, in Earth's magnetosphere, where solar wind field lines reconnect with Earth's field, and in solar flares where reconnection between magnetic loops on the Sun's surface releases the energy that accelerates solar energetic particles. But its operation at the scale of the helipause, producing a coherent region of connected field lines extending over millions of kilometers, was not anticipated in the theoretical models that guided the Voyager mission. The models had not included the possibility that the helipause could be a site of active reconnection, because they treated the two magnetic field systems as separate and the helipause as a stable boundary that simply kept them apart. The detection of the magnetic highway also revealed something important about the temporal dynamics of reconnection at the helipause. Voyager spent approximately 2 months in the highway before completing the crossing. The highway was not a transient feature lasting hours or days, as reconnection events at Earth's magnetopause typically last. It was a persistent, spatially extended region that existed for months. This persistence suggested that the reconnection geometry at the helipause is driven by large-scale, slowly evolving conditions. Perhaps the relative orientation of the interstellar magnetic field and the solar field, both of which change slowly, rather than by rapid, transient events. Understanding the detailed physics of reconnection at the helipause became one of the primary theoretical challenges of heliospheric science following Voyager's crossing, and the magnetic highway was the observational anchor for that entire research program. The implications extended beyond the heliopause itself. If magnetic reconnection creates direct connectivity between the solar field and the galactic field at the heliopause, the heliosphere is not as isolated from the interstellar environment as the models had assumed. Galactic cosmic rays can enter the heliosphere along reconnected field lines without the slow diffusion process that the models had assumed governed their penetration. Solar energetic particles can escape into interstellar space more efficiently through the same channels. The heliosphere leaks, and the leak is structured, determined by the geometry of reconnection at particular locations on the heliopause, rather than being uniform across the boundary. The magnetic highway showed that the solar system's interaction with the galaxy is more intimate, more direct, and more physically rich than any model had predicted. Interstellar space does not match the models. Voyager 1 became the first spacecraft to directly sample the interstellar medium when it crossed the heliopause in August 2012. Everything that was known about the physical properties of the local interstellar medium before that moment had come from remote observations. Spectroscopic measurements of absorption lines produced when the light from distant stars passed through the interstellar gas. Radio observations of interstellar hydrogen emission at the 21 centimetre wavelength, ultraviolet observations of various interstellar ion species, and theoretical models constrained by these indirect measurements. Voyager's direct in situ measurements were something qualitatively different, instruments physically immersed in the medium, measuring its properties from inside. The measurements that followed the heliopause crossing revealed a medium that differed from the models in several specific and scientifically significant ways. The electron density of the local interstellar medium, one of the most fundamental plasma properties, was measured through a technique that had not been anticipated in the original Voyager mission design. When a powerful solar eruption sends a pulse of energy outward through the heliosphere, that pulse compresses the helios-heath plasma, launches a pressure wave into interstellar space, and that wave travels through the interstellar plasma at the local sound speed. As the wave moves through the interstellar medium, it drives plasma oscillations, waves of compression and expansion in the electron density at the local plasma frequency, which depends directly on the local electron density. Voyager's plasma wave instrument, which was originally designed to study plasma waves in the solar wind and planetary magnetospheres, turned out to be capable of detecting these oscillations in the interstellar medium as well. The first detection of interstellar plasma oscillations occurred in October and November 2012, within weeks of the heliopause crossing, when a solar event from 2012 drove a wave into the interstellar medium that arrived at Voyager's location. The frequency of the oscillations gave an electron density of approximately 0.08 electrons per cubic centimetre. A second detection in April and May 2013 gave a slightly different value of approximately 0.065 electrons per cubic centimetre. A third event in 2014 gave approximately 0.10 electrons per cubic centimetre. The multiple measurements at slightly different times and slightly different locations revealed that the electron density in the local interstellar medium is not constant, but varies by roughly 20 to 30% over distances of a few astronomical units, a level of variability that the models had not captured. The average electron density from these measurements was consistent with the general range that remote observations had suggested for the local interstellar medium, a few tens of thousands of electrons per cubic metre. But the specific values differed from the best pre-crossing model estimates, and the variability was higher than models had assumed. The models had treated the local interstellar medium as relatively uniform in the immediate vicinity of the heliopause, based on the assumption that a homogeneous external medium would produce a more symmetric and stable heliosphere. Voyager's measurements indicated that the medium is significantly inhomogeneous, which would contribute to the asymmetries and instabilities in the Helopause structure that Voyager had already revealed. The temperature of the interstellar medium in the region immediately beyond the Helopause was inferred from the plasma measurements to be approximately 30,000 to 50,000 Kelvin, substantially higher than some pre-crossing model estimates, which had placed it closer to 6,000 to 7,000 Kelvin. This discrepancy might reflect the fact that the plasma immediately outside the Helopause is not representative of the broader local interstellar medium. It may be affected by the interaction with the heliosphere, heated by plasma waves or by reconnection processes at the Helopause, in ways that elevate its temperature above the ambient interstellar level. Alternatively, the pre-crossing temperature estimates based on remote spectroscopy may have been underestimates because of systematic effects in the spectral analysis. Resolving this discrepancy requires measurements from greater distances outside the Helopause, which only future missions will be able to provide. The magnetic field in the interstellar medium, as measured by Voyager 2's magnetometer after the November 2018 crossing, had a strength of approximately 5.5 nanotesla, similar to values inferred from interstellar polarization measurements and consistent with the general theoretical expectation for the local interstellar magnetic field. But the orientation of the field at Voyager 2's crossing location differed by approximately 36 degrees from the field orientation measured by Voyager 1 after its crossing, indicating that the interstellar magnetic field is not uniform at the scale of the distance between the two crossing points. Approximately 160 astronomical units of separation in different directions on the sky. This spatial variation in the interstellar magnetic field direction is physically reasonable and even expected given what is known about turbulence in interstellar magnetic fields. But it meant that the two Voyagers were sampling differently oriented field regions rather than two independent measurements of a single uniform background field. The overall picture that emerged from the first years of direct interstellar medium measurement by Voyager was of a medium that is qualitatively consistent with theoretical expectations, ionized, magnetized, at the general density and temperature range that remote observations had indicated. But that differs quantitatively from the specific models in ways that matter for understanding the structure and dynamics of the heliosphere. Every deviation from the model predictions, however small, represents a constraint on the specific physical conditions of the local interstellar medium that could not have been established through remote observation alone. The Voyager measurements will remain the foundational dataset for local interstellar medium characterization until a dedicated interstellar probe mission can provide more systematic and more extensive sampling of the medium beyond the Helopause. The tsunami waves from the Sun. Among all the unexpected discoveries that Voyager made in interstellar space, perhaps the most visually striking in its implications was the detection of what mission scientists called tsunami waves, pressure pulses driven through the interstellar plasma by powerful eruptions on the Sun's surface, detectable by a spacecraft more than 19 billion kilometers from the source. The discovery demonstrated that the Sun's influence extends far beyond the Helopause and far beyond any version of the heliosphere as it was previously understood, not as solar wind plasma, which is confined to the interior of the Helopause, but as mechanical disturbances propagating through the interstellar medium itself. The chain of events that produces a tsunami wave begins at the Sun's surface. During periods of elevated solar activity, the Sun produces coronal mass ejections, violent eruptions that blast billions of tons of magnetized plasma into the solar wind at velocities of several hundred to over 1,000 kilometers per second. These eruptions travel outward through the heliosphere as high-pressure pulses, compressing the solar wind ahead of them. The pulses travel much faster than the average solar wind because their pressure excess drives them through the surrounding plasma at supersonic speeds, creating their own shock fronts. When such a pulse, traveling outward at hundreds of kilometers per second, reaches the Helopause after a journey of months to years, it does not simply stop at the boundary. It collides with the heliopause and launches a corresponding pressure pulse into the interstellar medium beyond. The pulse that enters the interstellar medium is no longer a solar wind pulse. It is a wave of mechanical compression propagating through the interstellar plasma at that plasma's sound speed, which is approximately 60 kilometers per second in the local interstellar medium based on the temperature and density Voyager measured. This is far slower than the solar wind speeds involved in generating the pulse, but it is fast enough to cover significant distances across multiple astronomical units in a year. As this wave passes through the interstellar medium, it compresses the plasma, driving oscillations in the electron density that Voyager's plasma wave instrument can detect. The first tsunami wave detected by Voyager 1 was associated with a solar event that had occurred in March 2012, before Voyager crossed the heliopause. The pulse from this eruption travelled through the heliosphere, reached the heliopause in late 2012, and launched a wave into the interstellar medium that Voyager detected in October and November 2012, just weeks after the August 2012 heliopause crossing. The detection provided the electron density measurement described in the previous chapter, and it confirmed beyond any remaining doubt that Voyager had crossed into the interstellar medium. If the spacecraft had still been in the heliosheath, it would have detected a solar wind compression pulse rather than an interstellar plasma wave. The character of the detected signal, specifically its plasma frequency and the way the oscillations propagated, was unambiguous evidence that Voyager was now measuring interstellar plasma dynamics rather than solar wind dynamics. The second tsunami wave arrived in April and May 2013, associated with a series of solar eruptions in late 2012. The third arrived in March 2014, traced to eruptions in 2013. A fourth followed in 2015. Each wave provided an independent measurement of the local interstellar electron density at Voyager's position, and the small differences between successive measurements revealed the density variations in the medium discussed previously. Together, the four detections provided the most detailed characterization of local interstellar plasma properties ever obtained, derived from a measurement technique that nobody had anticipated would be available when the Voyager plasma wave instrument was designed in the early 1970s for the entirely different purpose of studying plasma environments in the solar wind and planetary magnetospheres. The scientific significance of the tsunami waves extends beyond the electron density measurements they enabled. The fact that solar eruptions can drive detectable mechanical disturbances through the interstellar medium demonstrates that the Sun's influence on its surrounding environment is not sharply bounded by the heliopause. The heliosphere is not a hermetically sealed bubble inside which all of the Sun's influence is confined. Rather, the boundary is permeable in multiple ways, to energetic particles through magnetic reconnection channels, to plasma waves through mechanical coupling, and presumably to electromagnetic radiation in all wavelength ranges that is not absorbed or scattered by the intervening plasma. The interstellar medium immediately surrounding the heliosphere is not a passive, undisturbed background against which the heliosphere sits. It is an active environment that responds to the Sun's activity, buffeted by tsunami waves from solar eruptions, in much the same way that Earth's ionosphere responds to solar ultraviolet radiation. On timescales governed by the crossing times for solar-driven disturbances to reach the heliopause and then propagate through the interstellar medium. This has implications for how we think about the interaction between stellar systems and the interstellar medium more generally. Our Sun is not the only star driving waves into the interstellar medium. Every active star with a stellar wind produces an astrosphere, the stellar analogue of our heliosphere, and every powerful eruption from any star launches disturbances into the surrounding interstellar medium. The interstellar medium is therefore not a quiet background, but an active, turbulent environment continuously stirred by the collective activity of all the stars within it. The Voyager measurements of tsunami waves gave us the first direct observational evidence of this stirring, confirmed at a level of physical detail that remote observations could never have provided. The magnetic field pointed the wrong direction. Of all the surprises that Voyager's crossing of the Helopause delivered, perhaps none generated more debate or required more creative theoretical work to explain than the behaviour of the magnetic field at and after the crossing. Before Voyager crossed the Helopause, virtually every model of the heliosphere predicted that crossing the boundary should produce a clear and significant change in the magnetic field direction. The heliospheric field, wound into the Parker spiral by the Sun's rotation, would be replaced by the galactic magnetic field, oriented independently based on the structure of the local interstellar medium and the large-scale topology of the galaxy's magnetic field. These two fields were expected to point in substantially different directions, so the crossing should produce a measurable rotation in the field as measured by Voyager's magnetometers. When Voyager 1 crossed the Helopause in August 2012, the magnetic field did not rotate. The direction of the field before the crossing and after the crossing were indistinguishable within measurement uncertainties. This result created months of genuine scientific confusion and was one of the primary reasons that the crossing itself was debated for over a year after it occurred. Some scientists argued that the absence of field rotation meant Voyager had not actually crossed the Helopause, despite the compelling evidence from the particle measurements. The debate was eventually resolved when scientists accepted that the galactic magnetic field in the region of Voyager 1's crossing happened, by coincidence, to be oriented approximately parallel to the heliospheric magnetic field at that location. This resolution is less contrived than it might initially appear. The heliospheric magnetic field at large distances from the Sun runs approximately parallel to the galactic plane in the radial outward direction from the Sun, and the local galactic magnetic field is also oriented roughly parallel to the galactic plane based on constraints from interstellar polarization measurements. Given that both fields are broadly parallel to the same large-scale structural feature, the galactic plane, it is not unreasonable that they would be approximately parallel in a specific local region. The coincidence is improbable but not impossible, and the evidence from all other instruments, the plasma density, the cosmic ray intensity, the particle species and energy distributions, made the Helopause crossing certain regardless of the magnetic field behaviour. Voyager 2's crossing in November 2018 provided a partial resolution to the coincidence hypothesis. Voyager 2's magnetometer did detect a rotation at the crossing, approximately 36 degrees over the course of the crossing interval. This rotation was smaller than most models had predicted for a typical crossing, but it was measurable and statistically significant, confirming that the heliospheric field and the interstellar field are indeed pointing in different directions, and that the coincidental alignment at Voyager 1's crossing location was a local feature rather than a property of the entire Helopause. The different field rotation at Voyager 2's location compared to Voyager 1's location is itself scientifically informative. It reveals that the interstellar magnetic field direction varies over the scale separating the two crossing points, consistent with the turbulent and inhomogeneous nature of the local interstellar medium that Voyager's other measurements had already suggested. The measurement of the interstellar magnetic field direction is of considerable importance for understanding galactic cosmic ray propagation and the structure of the local interstellar environment. Cosmic rays are charged particles, and charged particles in a magnetic field follow helical paths along field lines. The direction and coherence length of the interstellar magnetic field therefore determine the preferred directions from which cosmic rays arrive at the heliosphere and the efficiency with which they penetrate into the inner solar system. Models of galactic cosmic ray propagation, which underlie predictions of radiation exposure for astronauts in deep space, and interpretations of the cosmic ray isotope record in geological archives on Earth, depend critically on the properties of the interstellar magnetic field in the solar neighbourhood. Voyager's direct measurements of this field, limited as they are to 2 specific locations, are the only in situ constraints on the field strength and direction in the local interstellar medium that exist. The field measurements also constrain models of the heliosphere's interaction with the interstellar medium. The efficiency of magnetic reconnection at the Helopause, which produces the magnetic highway discussed in a previous chapter, depends on the relative orientation of the heliospheric field and the interstellar field. Where the 2 fields are anti-parallel, reconnection proceeds most efficiently. Where they are parallel, reconnection is suppressed. The fact that Voyager 1 detected a strong magnetic highway signature, despite the roughly parallel field orientation at its crossing location, suggests that reconnection geometry is more complex than the simple anti-parallel model assumes, involving small-scale field variations that enable reconnection even when the large-scale fields are approximately parallel. This complexity is now an active area of theoretical research that began from Voyager's unexpected field measurements. Cosmic rays come from the wrong places. Galactic cosmic rays, high-energy charged particles, primarily protons and heavier atomic nuclei, accelerated to energies ranging from millions to trillions of electron volts by astrophysical processes throughout the galaxy, are among the most energetically important components of the interstellar medium. They carry approximately as much energy density as the magnetic field, the thermal plasma, and the turbulent motions of the interstellar medium, making them a dynamically significant constituent rather than a minor perturbation. They are produced by supernova remnants, pulsar wind nebulae, relativistic jet sources, and other violent astrophysical events, and they propagate through the galaxy, diffusing along and across the galactic magnetic field lines over timescales of millions of years, before either escaping the galaxy or losing their energy to various processes. Before Voyager crossed the Helopause, measurements of cosmic rays inside the heliosphere were already revealing hints that the directional distribution of cosmic ray arrivals was not uniform. Cosmic rays arriving from different directions had slightly different intensities, more from some directions, fewer from others, suggesting that the local interstellar environment was not a simple isotropic sea of cosmic rays, but had some directional structure. These pre-crossing measurements were difficult to interpret cleanly because the heliospheric magnetic field modulates and distorts the cosmic ray distribution before it reaches the inner solar system, making it hard to separate the true interstellar anisotropy from the heliospheric filtering effect. After Voyager crossed the Helopause and began measuring the cosmic ray environment in the interstellar medium directly, the directional anisotropy became a definitive observational fact rather than a suggestion. Cosmic rays arriving at Voyager's position were not equally intense from all directions. There was a clear enhancement from some directions and a corresponding deficit from others, with an anisotropy amplitude of approximately 1% in the most energetic particle channels. 1% sounds small, but in the context of isotropic cosmic rays, it is a large and statistically overwhelming signal that carries clear information about the structure of the local cosmic ray sources and propagation pathways. The most counterintuitive aspect of the cosmic ray anisotropy was the deficit from the direction of the galactic center. Naively, one might expect the highest cosmic ray intensity to come from the direction of the galactic center, the region of the Milky Way, with the highest stellar density, the highest supernova rate, and therefore the most intense source of cosmic ray production. Instead, Voyager measured a relative deficit in the galactic center direction, suggesting that cosmic rays produced in the inner galaxy are less able to propagate outward to the solar neighborhood than cosmic rays produced in the outer galaxy or in more immediate local sources. The explanation most consistent with cosmic ray propagation theory involves the galactic magnetic field being stronger and more tangled in the inner galaxy, causing cosmic rays produced there to diffuse more slowly and be more likely to lose energy before escaping to the solar neighborhood. Meanwhile, nearby sources, old supernova remnants within a few hundred light-years of the Sun, may be contributing disproportionately to the local cosmic ray population, creating the observed anisotropy pattern. The directional distribution also showed enhancements from the directions consistent with known local interstellar features, particularly the boundary of the local bubble, a cavity in the interstellar medium approximately 300 light-years across, within which the Sun is located, carved out by supernova explosions within the past few million years. The boundary of the local bubble is a region of enhanced density and magnetic field strength, where interstellar plasma from the denser surrounding medium is compressed against the bubble's edge. Supernova remnants near this boundary could be accelerating cosmic rays more efficiently than sources in the low-density interior, and those cosmic rays would then stream into the interior, including to Voyager's measurement location, from the direction of the bubble's boundary. The cosmic ray measurements from Voyager are the first direct characterization of the cosmic ray directional distribution in the local interstellar medium, free from the distorting effects of the heliosphere. They provide constraints on the sources and propagation of cosmic rays in the solar neighborhood that remote measurements, which measure cosmic rays after they have been processed by the heliospheric magnetic field, cannot provide. The data are already being used to refine models of local cosmic ray propagation and to identify the contributions of specific nearby sources to the local cosmic ray population. These models, in turn, affect predictions of radiation exposure in the interstellar medium that will be relevant for planning future crewed missions beyond the heliosphere and for interpreting the geological and biological record of cosmic ray exposure on Earth over its history. What the Voyagers mean for interstellar travel. The Voyager discoveries at the edge of the solar system and in the interstellar medium have direct and sobering implications for the long-term human aspiration to travel beyond our solar system. Voyager itself is traveling at approximately 17 kilometers per second, about 61,000 kilometers per hour relative to the Sun. This is the fastest speed that any human-made object has achieved through conventional rocket propulsion combined with gravitational assists, and it took a once-in-176 years planetary alignment to achieve it. At this speed, Voyager has covered approximately 24 billion kilometers in 49 years. Proxima Centauri, the nearest star to the Sun, is approximately 40 trillion kilometers away. At Voyager's speed, the journey would take approximately 73,000 years. That number alone is sufficient to establish the fundamental challenge of interstellar travel at any speed achievable with chemical or nuclear propulsion systems that are extensions of current technology. But Voyager's discoveries add several additional dimensions to the challenge that go beyond the simple problem of travel time. The first is the radiation environment of the interstellar medium. Voyager measured galactic cosmic ray intensities in the local interstellar medium at approximately twice the level measured in the inner solar system. The heliosphere provides partial shielding that reduces the cosmic ray flux experienced by planets and spacecraft within it. For a crewed spacecraft traveling through the interstellar medium, this elevated cosmic ray exposure would represent a significant long-term radiation dose to crew members, even at the relatively low intensities measured in the local interstellar medium. At the energies characteristic of galactic cosmic rays, typically millions to billions of electron volts per nucleon, the particles penetrate deeply into matter, including biological tissue, depositing ionizing radiation that damages DNA and increases cancer risk. Shielding against galactic cosmic rays is much more difficult than shielding against the lower energy solar energetic particles that are the primary radiation hazard for astronauts in the inner solar system, because the high energies allow cosmic rays to penetrate any physically reasonable thickness of shielding material. A massive shielding sufficient to meaningfully attenuate galactic cosmic rays would be prohibitively heavy for any spacecraft designed to travel at significant fractions of the speed of light. The second challenge is the density of the interstellar medium itself. Voyager measured an electron density of approximately 0.08 per cubic centimetre in the local interstellar medium, which sounds negligible, and at Voyager's speed genuinely is negligible, since the spacecraft encounters so few atoms per second that their cumulative effect on the spacecraft structure is unmeasurable. But at velocities approaching the speed of light, the velocities that would make interstellar travel feasible on human timescales, the situation changes dramatically. At 10% of the speed of light, approximately 30,000 kilometers per second, each atom of interstellar hydrogen that a spacecraft encounters arrives with a kinetic energy of approximately 6 electron volts in the spacecraft's reference frame. At 50% of the speed of light, the kinetic energy per hydrogen atom exceeds 50 million electron volts, enough to cause significant radiation damage with every impact. The interstellar medium that is completely benign at Voyager's speed becomes a severe radiation and erosion hazard at the speeds required for interstellar travel on human timescales. The discovery of tsunami waves from solar eruptions propagating through the interstellar medium adds a third hazard that had not been anticipated before Voyager's measurements. The interstellar medium is not a quiet, static environment. It is continuously stirred by pressure waves from stellar activity throughout the galaxy, and an interstellar spacecraft would encounter these waves as transient periods of elevated plasma density and possibly elevated cosmic ray intensity. The Voyager detected tsunami waves from solar eruptions are relatively mild examples of this type of disturbance. A shock wave from a nearby supernova or a powerful outburst from a magneta could potentially drive much more intense disturbances through the local interstellar medium with little or no advance warning. An interstellar spacecraft would need robust protection against these transient environmental hazards, in addition to the steady-state radiation environment. The magnetic field measurements from Voyager also revealed that the interstellar magnetic field is neither uniform nor predictable from outside the Helopause. The field direction differs by 36 degrees between Voyager 1 and Voyager 2's crossing locations, a spatial variation over roughly 160 astronomical units of separation. A spacecraft traveling through the interstellar medium would encounter continuously varying magnetic field conditions that would affect the trajectories of charged particle accelerators, the performance of any plasma propulsion systems that interact with the ambient field, and the overall radiation environment experienced by the crew. Mapping the interstellar magnetic field along a proposed interstellar route would require extensive prior reconnaissance that exceeds anything currently planned. Despite all these challenges, Voyager's discoveries are fundamentally enabling for interstellar mission planning because they replace theoretical estimates with direct measurements. Before Voyager, mission planners designing a hypothetical interstellar probe had to rely on models of the interstellar environment that were ultimately constrained by the same indirect observational methods that Voyager's discoveries showed were systematically wrong. Now, at least for the specific region of the interstellar medium immediately beyond the Helopause, there are actual measurements. The electron density is known. The magnetic field strength and direction are measured. The cosmic ray intensity and its directional distribution are characterized. The dynamic variability of the medium, the tsunami waves, the density fluctuations, is documented. This measured baseline is the starting point for designing the next generation of interstellar missions with realistic environmental models, rather than optimistic theoretical constructs. The Golden Record. On each of the two Voyager spacecraft, attached to the body of the probe and designed to survive for billions of years in the vacuum of space, is a 30-centimetre gold-plated copper disc, a phonograph record containing 90 minutes of audio 116 images encoded as audio signals, greetings in 55 languages, and mathematical and physical diagrams intended to enable an intelligent recipient to locate Earth and decode the record's contents. The Golden Record is the most audacious act of communication in human history, a message from one species to any other that might exist in the universe, carried by machines that will drift through interstellar space for billions of years. The record was the brainchild of Carl Sagan, who persuaded NASA to include it on the Voyager missions as a gesture of goodwill and an expression of human curiosity and creativity. Sagan assembled a committee that included astronomer Frank Drake, artist and designer Linda Salzman Sagan, writer Anne Druyan, scientist Timothy Ferris, and artist John Lomberg, who worked under extraordinary time pressure. The records had to be completed and installed on the spacecraft before the launch windows opened, to make choices about what to include that would represent the full scope of human civilization and experience. The sounds were chosen for their universality and their distinctiveness. Natural sounds, the wind in trees, ocean surf, thunder, rain, convey information about Earth's weather and atmosphere. Animal sounds, whale song, bird calls, crickets, dogs, convey the richness of the biosphere. Human sounds, a heartbeat, breathing, footsteps, laughter, a mother comforting a child, convey something of the biology and social nature of the species that built the spacecraft. And music, 90 minutes of it spanning cultures from around the world and periods from ancient to contemporary, conveys the aesthetic dimension of human experience that neither science nor language alone can fully express. The music selection was perhaps the committee's most agonizing task. They chose Johann Sebastian Bach's Brandenburg Concerto No. 2 in F major, reasoning that the mathematical precision and emotional depth of Bach's counterpoint represented human intellectual achievement at its most universal. They included Beethoven's Fifth Symphony and his string quartet Opus 130, Mozart's The Magic Flute, and Stravinsky's The Rite of Spring from the Western classical canon. But the committee was acutely aware that selecting only Western classical music would be a profound misrepresentation of human musical culture. They added Javanese gamelan music for its intricate interlocking rhythmic patterns, Georgian polyphonic choir singing for its dense harmonic textures, Pygmy music from Zaire for its distinctive vocal style, Aboriginal songs from Australia representing one of the oldest continuous musical traditions on Earth, Azerbaijani bagpipe music, Indian classical ragas, Chinese Guqin music, and Peruvian panpipe music. They added Chuck Berry's Johnny B. Good, a decision that prompted John Lennon to reportedly say he was glad rock and roll had made it onto the record, Louis Armstrong's Melancholy Blues, and a Bulgarian folk song. The 116 images encoded on the record range from mathematical and physical diagrams explaining the metric system, the solar system, DNA structure, and human anatomy, to photographs of landscapes, cities, people working and playing, and the diversity of human cultures. There are images of the Great Wall of China and the Sydney Opera House, of children playing and elderly people resting, of food being prepared and eaten, of athletes and musicians and scientists at work. The committee debated extensively about whether to include images showing human conflict, poverty, and environmental destruction, whether to present an idealized picture or an honest one. They ultimately chose to emphasize what humanity aspired to rather than what it had done wrong, while including enough diversity and complexity to suggest that human civilization was not simple or uniform. The greetings in 55 languages, from ancient Akkadian to modern Mandarin, English, Arabic, Spanish, and dozens of others, each offered brief messages of welcome and goodwill in the speaker's native tongue. UN Secretary-General Kurt Waldheim contributed a greeting on behalf of humanity. The then President of the United States, Jimmy Carter, sent a letter that was also included, expressing hope that the Voyager craft would encounter intelligence that could decipher the record and receive humanity's greetings in the spirit in which they were offered. The record's cover contains instructions for its use, etched in aluminum that will survive for billions of years in space. These instructions are entirely non-linguistic. They use diagrams and mathematical notation that any intelligence capable of detecting and examining the record would presumably understand. The cover shows the position of Earth relative to 14 pulsars, using the precise rotational periods of those pulsars as cosmic clocks and distance markers that uniquely specify Earth's location in three-dimensional space and in time. It shows how to play the record and at what rotational speed. It shows how to decode the encoded images from the audio signal. And it shows the electromagnetic transition of hydrogen, the most abundant element in the universe, and a reference frequency that any civilization with radio astronomy would recognize to specify the unit of time used in the record's timing information. The probability that the golden record will ever be found and decoded is effectively zero. The Voyager spacecraft are tiny objects, a few meters across, in the incomprehensible vastness of interstellar space. The probability that either spacecraft will pass within the planetary system of any star within the next million years is vanishingly small. Even if a spacecraft did pass near another star system, the probability that an intelligent civilization capable of detecting and retrieving it exists there is unknown, but almost certainly small. Carl Sagan acknowledged this explicitly. The record was not, he said, a serious attempt at interstellar communication. It was a statement of intent, a declaration that humanity had looked outward, had chosen to send a message rather than silence, and had committed to the belief that the universe was worth communicating with. The record's value was in the making of it, not the receiving. It forced the committee, and through them humanity, to ask what was worth preserving, what was essential about human experience, and to commit to an answer. The answer is there, attached to two spacecraft drifting through interstellar space, carrying the music and the greetings, and the images of a species that once looked at the stars and decided to reach toward them. The end of the mission. Both Voyager spacecraft are dying. The process is gradual and predictable. The mathematics of radioactive decay is precise, and the engineers at the Jet Propulsion Laboratory have known for decades exactly how the power budget would evolve, and approximately when each system would need to be shut down. What could not be predicted with certainty was which systems would fail before they were deliberately switched off, which would continue operating beyond their design temperatures and specifications, and which decisions would ultimately determine what the final transmitted measurements would be. The power situation as of 2026 is critical. Voyager 1's 3 radioisotope thermoelectric generators are producing approximately 249 watts, down from the approximately 470 watts available at launch 49 years ago. The spacecraft's total power consumption for all operating systems, the transmitter, the attitude control systems, the computer systems, the instrument heaters, and the instruments themselves, requires approximately 245 watts. The margin is approximately 4 watts. This means that essentially any additional failure of any system that increases power consumption, or any requirement to operate a heater that had been switched off to conserve power, could exceed the available budget and force an unplanned shutdown of something critical. The engineers responsible for keeping Voyager operational have been making triage decisions for years. In 2019, the heater for the instrument used to detect cosmic rays on Voyager 2 was switched off to conserve power. The instrument's temperature dropped to approximately -59 degrees Celsius, 40 degrees below its design operating temperature. Instruments, like all electronic components, are designed to operate within specific temperature ranges, and operating below the design minimum can cause materials to become brittle, contacts to become resistive, and electronic components to behave erratically or fail. The engineers expected the cosmic ray instrument to fail. Instead, it continued to return data, apparently undamaged by the extreme cold. The 1970s engineering, built with significant margins against uncertainty, had proven robust in ways that even the original designers had not anticipated. Similar decisions have played out for both spacecraft. Heaters for instrument booms have been switched off, allowing the booms to cool to whatever temperature the spacecraft's equilibrium with the cosmic background radiation and the sun's faint warmth determines. Scientific instruments that were consuming power without returning high-priority data have been switched off permanently. The onboard computers are now running simplified, stripped-down versions of their original software, optimized for the minimal set of operations needed to keep the spacecraft pointing its antenna at Earth and returning the key plasma, magnetic field, and cosmic ray measurements that are scientifically irreplaceable. By approximately 2027 or 2028, the power budget will be insufficient to operate any science instrument at all, while simultaneously maintaining the transmitter and the attitude control systems. At that point, engineers will face the final decision: which instrument gets the last allocation of power before the transmitters must be shut down. The plasma wave instrument, the magnetometer, and the cosmic ray instrument are the three most scientifically valuable systems for monitoring the interstellar medium, and the choice among them will reflect a judgment about which measurement is most irreplaceable. Whatever the decision, the last transmission from each spacecraft will be a reading of some interstellar property: plasma density, magnetic field strength, cosmic ray intensity, taken at a distance that no other spacecraft will match for decades. After the transmitters fall silent, the spacecraft will continue traveling outward at approximately 17 kilometers per second indefinitely. There is no friction in interstellar space to slow them. No force will decelerate them significantly on any timescale relevant to human civilization. They will drift outward through the interstellar medium, through the slowly increasing density of the Oort cloud, the vast shell of icy bodies extending from roughly 2,000 to perhaps 100,000 astronomical units, for thousands of years. The outer edge of the Oort cloud represents the practical limit of the Sun's gravitational influence over objects on long timescales, and Voyager will not exit even the inner Oort cloud for approximately 300 years, or the outer Oort cloud for approximately 30,000 years. In approximately 40,000 years, Voyager 1 will pass within approximately 1.6 light-years, roughly 500 times the Earth-Sun distance, of the star Gliese 445, a dim red dwarf in the constellation Camelopardalis. Voyager 2 will pass within approximately 1.7 light-years of the star Ross 248, another red dwarf in Andromeda, at approximately the same time. Neither spacecraft will enter the planetary systems of these stars if they exist. The closest approaches are far too distant for any gravitational interaction that would meaningfully deflect either spacecraft. They will simply drift past, silent, cold, and intact, carrying their golden records through a region of space no human or human-made object has ever occupied or will occupy for thousands of generations to come. Interstellar Probe. The approaching end of the Voyager program forces a question that has been building quietly for years. What comes after humanity's first step into interstellar space? For decades, the twin spacecraft Voyager 1 and Voyager 2 have traveled farther than anything ever built, transforming from planetary explorers into the only functioning laboratories beyond the Sun's direct influence. Their data reshaped our understanding of where the solar system ends and how it interacts with the galaxy beyond it. But they were never designed for this role. They became interstellar probes by circumstance, not by design. What they discovered now demands a mission built specifically for that purpose. The scientific community has already outlined what that mission should be. Through multiple decadal survey reports organised by the National Academy of Sciences, researchers have identified a dedicated interstellar probe as the next major step in heliophysics. The reasoning is simple. Voyager provided 2 data points taken along 2 trajectories in one region of space. From those limited observations, scientists have attempted to reconstruct the structure of an enormous boundary surrounding the entire solar system. That is not enough. The heliosphere is not a smooth shell. It is a 3-dimensional, constantly evolving structure shaped by the solar wind, magnetic fields, and the surrounding interstellar medium. The boundary itself, known as the Helopause, is where the outward pressure of the solar wind balances against the pressure of interstellar space. Before Voyager reached it, models predicted a relatively simple transition. Instead, the data revealed something far more complex. Plasma densities changed in unexpected ways. Magnetic fields did not behave as predicted. The transition region appeared structured, uneven, and strongly influenced by conditions outside the solar system. These findings did not just refine existing theories, they forced scientists to rethink them entirely. But the limitations of Voyager are just as important as its discoveries. Both spacecraft are travelling in roughly similar directions relative to the heliosphere. That means we still lack information about how the boundary behaves in other regions, especially along the nose, where the solar system moves through interstellar space, and along the extended tail trailing behind it. Without measurements in those directions, scientists cannot fully map the heliosphere's shape or understand its dynamics. It is like trying to understand an entire ocean using data from 2 drifting sensors. A dedicated interstellar probe would change that. Unlike Voyager, it would be designed from the beginning to study the heliosphere and the interstellar medium beyond it. The concept, developed by the Johns Hopkins Applied Physics Laboratory, envisions a spacecraft capable of travelling much faster and much farther than its predecessors. The goal is to reach a distance of 500 astronomical units from the Sun within about 50 years. For comparison, Voyager 1, after nearly half a century, has reached just over 150 astronomical units. Achieving that kind of performance requires a major increase in speed. The proposed mission would rely on a combination of a powerful launch system and advanced trajectory design. One of the key techniques involved is based on the Oberth effect, a principle of orbital mechanics that allows a spacecraft to gain more energy by firing its engines at the point where it is moving fastest. In this case, that point would be extremely close to the Sun. The spacecraft would dive inward, approaching within a few solar radii of the Sun's surface, and then ignite a propulsion stage at that moment. Because of the high speed at that point, the energy gained from the burn would be maximized, sending the spacecraft outward at a velocity far greater than what could be achieved using conventional methods. This type of maneuver is no longer theoretical. The Parker Solar Probe has already demonstrated that spacecraft can survive extremely close passes to the Sun using advanced heat shields and thermal protection systems. The Interstellar Probe would build on that experience, combining it with modern propulsion techniques to achieve the speeds required to leave the heliosphere much more quickly than Voyager ever could. Speed, however, is only part of the mission. The real advantage of a next-generation probe lies in its instruments. Voyager's scientific payload was revolutionary for its time, but it reflects the limitations of 1970s technology. A modern spacecraft could carry far more sensitive and capable instruments. Plasma analyzers would measure particle velocities, densities, and temperatures with much higher precision, revealing fine details in the behavior of both solar and interstellar plasma. Magnetometers would provide accurate measurements of magnetic field strength and direction, allowing scientists to study turbulence and magnetic interactions at the boundary in far greater detail. Energetic particle detectors would extend these capabilities by analysing cosmic rays and other high-energy particles as they move through the heliosphere. These measurements are critical for understanding how the Sun shields the solar system from galactic radiation. In addition, the spacecraft could carry mass spectrometers capable of directly sampling the composition of the interstellar medium. This would provide insights into the chemical makeup of the region of space surrounding our solar system. One of the most important additions would be the ability to image the heliosphere itself. Using ultraviolet observations, particularly in the Lyman alpha wavelength, the probe could map the distribution of neutral hydrogen just outside the Helopause. This region, often referred to as the hydrogen wall, forms where interstellar hydrogen accumulates as it interacts with the solar wind. By observing it, scientists could effectively create the first large-scale image of the heliosphere from the outside that would transform our understanding of its shape, size, and orientation. The mission could also include instruments designed to study interstellar dust. These tiny particles carry information about processes occurring throughout the galaxy, including star formation and the distribution of organic material. Measuring their size, composition, and motion would provide valuable data about the environment beyond the solar system. Beyond these direct scientific goals, the Interstellar probe opens the door to more ambitious possibilities. One of the most intriguing is the use of the Sun as a gravitational lens. According to general relativity, a massive object like the Sun can bend and focus light from distant sources. At distances of around 550 astronomical units and beyond, this effect becomes strong enough to act like a natural telescope. A spacecraft positioned at that distance could, in principle, use this effect to observe distant objects with extraordinary resolution. This concept has profound implications. It could make it possible to directly image planets orbiting nearby stars, potentially revealing surface features or atmospheric details. Achieving this would require extremely precise positioning and advanced optical systems, but the physics is well understood. Reaching the required distance is the main challenge, and that is exactly what the Interstellar probe is designed to accomplish. Despite the strength of the scientific case, the mission is not guaranteed to happen. Its future depends on decisions made within NASA and the broader scientific funding environment. The estimated cost, roughly $1 to $2 billion, places it in competition with other major missions. These include planetary exploration projects, Earth science programs, and other heliophysics initiatives. Each of these has its own priorities and constraints. Another challenge is the mission's timescale. Unlike missions that deliver results within a few years, the Interstellar probe would take decades to reach its primary scientific targets. That requires long-term planning and sustained commitment across multiple generations of scientists and engineers. It also raises practical questions about maintaining mission operations, preserving technical expertise, and ensuring continuity over long periods. However, there are strong arguments for moving forward sooner rather than later. The Voyager spacecraft are still operating, but their power supplies are declining, and their instruments are gradually being turned off. Once they fall silent, the only direct measurements of the Helopause and nearby interstellar medium will come from the data already collected. Without a successor mission, progress in this field will slow significantly due to the lack of new observations. There is also a broader benefit to consider. Developing the Interstellar probe would drive advancements in propulsion systems, power generation, and deep space communication. These technologies would support future exploration efforts across the solar system and beyond. In that sense, the mission is not just about answering specific scientific questions. It is about expanding humanity's ability to explore deep space. The Voyager mission began as an opportunity, taking advantage of a rare planetary alignment to explore the outer planets. Its transformation into an interstellar mission was unexpected. The Interstellar probe represents the opposite approach. It is a deliberate effort to continue that journey, guided by what Voyager has already revealed. At its core, the case for the Interstellar probe is about continuity. Voyager showed that the boundary of the solar system is more complex and more dynamic than previously believed. It revealed that our models were incomplete and that the interaction between the Sun and the galaxy is an active process. Those discoveries raise new questions that cannot be answered with existing data. A dedicated mission would turn those questions into a structured scientific program. It would map the heliosphere in multiple directions, measure its interaction with the interstellar medium in detail, and extend our reach deeper into space than ever before. It would take the next step in understanding not just our solar system, but how stars interact with their surrounding environments across the galaxy. The technology exists, the scientific goals are clear, the need for the mission has been established. What remains is the decision to move forward. As the signals from Voyager grow weaker and its instruments approach the end of their operational lives, the urgency of that decision becomes harder to ignore. The next step is not limited by physics or engineering. It is defined by choice, still teaching us. 2 spacecraft launched in 1977 with less computing power than a modern smoke detector, designed for a 5-year mission to Jupiter and Saturn, are still transmitting data from interstellar space in 2026. The fact that this sentence is true, that it describes the actual world rather than a science fiction premise, is perhaps the most remarkable thing in the entire Voyager story. The engineering that made it possible was extraordinary. The science that resulted was revolutionary, and the spirit of inquiry that drove it, the willingness to send instruments into the unknown and trust the data they returned, even when the data contradicted decades of careful theoretical work, is the best example available of what the scientific method looks like when it is practiced at its most ambitious and its most honest. The 7 discoveries that Voyager made at the edge of the solar system share a common character. Each one was not a case where the models were completely wrong. The basic physics of the Helopause, the termination shock, the heliosheath, and the interstellar medium were all correctly described in their general features. What the models got wrong was the specific numbers, the detailed structure, and the particular phenomena that emerge from the interaction of the solar wind with the interstellar medium at the level of detail that only direct measurement could reveal. The Helopause was not at 90 to 100 astronomical units. It was at 121 and 119 astronomical units in different directions. The heliosphere was not symmetric. It was asymmetric in ways that reflected the Sun's motion through the local interstellar medium. The transition was not clean and rapid. It was prolonged, complex, and structured with a magnetic highway that nobody had predicted. The interstellar medium properties were close to model estimates, but not identical. The tsunami waves were entirely unanticipated. The magnetic field orientation coincidentally aligned in one direction and was measurably different in another. The cosmic ray anisotropy revealed structure in the local source environment that isotropic models could not capture. Each of these discrepancies between model and measurement is not a failure of science. It is science working correctly. The models were built from the best available data and the most carefully applied physics. They made predictions. The predictions were tested. The tests revealed ways in which the models were incomplete. The models are now being revised. New predictions will emerge. New tests will follow. This is the cycle that has driven every advance in human understanding of the physical world, from Newton's laws of motion to quantum mechanics, from the geocentric universe to the Big Bang, from static continents to plate tectonics. The Voyager spacecraft fit into this cycle as one of its most dramatic and most productive episodes. A test of theoretical understanding that was thorough, was unambiguous and was profoundly informative about the ways in which the real universe is richer and stranger than the best available models described. The pale blue dot photograph taken by Voyager 1 on February 14, 1990, looking back at Earth from 6 billion kilometres away, showing our planet as a mote of dust suspended in a sunbeam against the backdrop of deep space, remains one of the most powerful images ever produced. Carl Sagan's reflection on that photograph about how it challenges every assumption of human specialness and every pretense of cosmic significance has been quoted countless times in the decades since. What is less often noted is the relationship between that photograph and the discoveries that followed. The spacecraft that took that picture of Earth's smallness went on to cross the Helopause to measure the properties of the interstellar medium for the first time, to discover the magnetic highway and the tsunami waves and the asymmetric heliosphere. The same instruments that documented human smallness relative to the cosmos also documented how much more complex the cosmos is than humans had imagined. Looking outward and being humbled by what we find is not the same as being defeated by it. It is the beginning of understanding. Both Voyagers will fall silent within a few years, and the questions that the Voyagers could not answer about the full three-dimensional structure of the heliosphere, about the properties of the interstellar medium at distances of hundreds of astronomical units, about what lies in the heliospheric tail, about the Sun's gravitational lens at 550 astronomical units, will remain open, waiting for the next mission that dares to go and look. The universe does not owe us simple answers. The Voyagers proved that conclusively, and proved it in the most productive possible way, by finding that reality was more complex, more structured, and more interesting than the best theories available. That is not a warning. It is an invitation.